Watch a chess grandmaster play a simultaneous exhibition. They move from table to table, glancing at each board for only a few seconds before making a move and continuing on. Often, they defeat a dozen opponents at once. Observing this, we tend to credit the grandmaster with immense real-time processing power. We assume they are computing thousands of potential future moves and countermoves in a single glance. This assumption aligns with the theory of means-ends analysis, the idea that high-level expertise is driven by a faster, more complex engine for generating novel strategies on the fly. Cognitive research has proven this is not the case. The grandmaster is not standing at each board calculating novel strategies or thinking through an unprecedented chain of events. Ironically, the novices are the ones engaged in exhausting problem-solving. Because they lack pre-existing knowledge of the specific board states, they must try to calculate every move from scratch. The grandmaster's dominance is not the result of superior real-time calculation. It is driven by an entirely different cognitive mechanism. To understand how the human brain manages complexity, we can look to the baseline example of a natural information processing system: biological evolution. Evolution handles highly complex and unpredictable environments by relying on a massive database, the genome. This store of genetic information determines the activities of an organism, passing successful adaptations down through generations. Human cognitive architecture follows this same blueprint. Just as evolution relies on the genome to navigate a complex world, human cognition relies on an immeasurably large long-term memory store. Long-term memory is frequently viewed as a passive ledger for past events. However, it functions as the active engine of high-level cognition. This is the information store principle, the requirement of an immense database to navigate environmental complexity without failing. Human intelligence operates as a massive storage and retrieval system, providing the foundation for how we actually learn and solve problems. Psychologist Adrian de Groot attempted to isolate exactly what makes a grandmaster superior. He tested if they searched deeper into future moves or broader across alternatives than average players. De Groot found no such advantage. Grandmasters showed no superiority in problem-solving depth or breadth compared to average players. He then tested their memory. He showed players real chessboard configurations for 5 seconds and asked them to recreate the boards from memory. On real game configurations, grandmasters achieved nearly 90% accuracy, while novices performed poorly, recalling only a few pieces. Chase and Simon later modified this using randomized boards with no logical structure. Facing random data, grandmaster performance plummeted. They were no better than the novices. This indicates that expertise is not a generalized thinking skill. If it were, it would have applied to the random boards. Instead, it is strictly limited to recognizable patterns. Herbert Simon concluded that a grandmaster has between 10,000 and 100,000 specific board configurations stored in their long-term memory. Building this database requires a decade of deliberate practice. This allows grandmasters to instantly retrieve the best move for a recognized pattern without needing to calculate a new strategy. These findings extend beyond chess. Patterns of domain-specific memory are found in computer programming, electronic engineering, and the comprehension of complex text. What we perceive as rapid problem-solving is actually instantaneous pattern matching from long-term memory. The way this information is organized is explained by schema theory, which stems from the early work of researchers like Jean Piaget. A schema is a cognitive construct that classifies multiple elements of information into a single, unified element based on how those elements are used. Consider an algebra problem: A divided by B equals C. Solve for A. A novice sees 5 distinct elements that must be processed individually. An expert, however, sees the entire equation as a single schema. For the expert, that single schema immediately triggers the automated action of multiplying both sides by B. Through extensive practice, these schemas become automated, allowing them to operate without conscious effort. This is how we read. We no longer process individual letters. We automatically recognize entire words and sentences through automated schemas. Schemas act as cognitive templates, allowing us to bypass the severe limits of conscious thought and render complex problems effortless. This architecture explains why programming a computer to play grandmaster chess is easy, yet programming a robot to pick a flower is impossible. Skills like spatial navigation and object recognition are biologically primary. We evolved to acquire these massive databases of information automatically and unconsciously. Simple physical tasks appear easy only because we possess a massive store of primary knowledge in long-term memory dedicated to them. Biologically secondary knowledge includes cultural inventions, like the game of chess, calculus and mathematics, and reading text. These are skills we have not evolved to learn automatically. Computers excel at secondary knowledge because the rules are finite. They fail at primary knowledge because the required database of variables is too fast to easily program. The perceived simplicity of primary tasks is an illusion created by the vast knowledge base required to execute them. A massive store of information is the true driver of both physical movement and abstract thought. This cognitive architecture carries direct implications for how we design instruction and structure education. Many modern educational trends prioritize domain general skills or inquiry-based learning. The focus is often on teaching students how to think rather than what to know. However, general problem-solving strategies such as means-ends analysis are biologically primary knowledge. Humans acquire these strategies automatically and unconsciously. They do not need to be formally taught in a classroom. Attempting to apply a general strategy to a subject without specific schemas leads to failure, as seen with the randomized chessboards. Without domain knowledge, the brain has no patterns to match. Instructional methods that ignore the amassing of domain-specific schemas waste cognitive effort on generic skills that students already possess. De Groot's work with Grandmasters establishes a clear rule. In any biologically secondary domain, the primary difference between a novice and an expert is the specific knowledge held in long-term memory. The explicit purpose of all instruction is to increase the store of domain-specific schemas in the learner's long-term memory. Overarching theories are of little use if the learner has not memorized the countless problem states and associated actions that define expertise. If an instructional procedure cannot describe exactly what has changed in long-term memory, it runs the risk that nothing has been learned. Real expertise is not a product of clever processing. It is exclusively the result of a meticulously built and massively accumulated information store.